Today on the must recap about the binary search tree, and this is the content I'm gonna cover. I'm gonna make to cover about the definition and some basics about implementation with the binary search tree. So first, what is the binary search tree? And for my memory, for the normal tree, right? And it can have like multiple sub node, right? The one node can have like multiple tri node. This is what we call the tree, like when one node hold reference for multiple node. But for the binary search tree, it's just limited to contain like two node, the left and the right. This is what we name it the left and the right, and it must follow the rule that the data of the parent node is greater than the left node and less than the right node. For example, for my node, I want to contain the integer, and right now I insert like for the root node. For the parent, I want to insert like for the 5, so the left node must less than 5, so it must be like 4, 3, 2, 1, anything, but it must less than 5. If it's like greater than 5 right now, for example like 7, it's like break the rule of the binary search tree. So for example right now insert 4 right here, and for the right side it's much greater than the parent, because the parent is 5, so the right side must be like 6, 7 or anything must be greater than 5. But if less than 5, for example like 4, for example like 3, right, it's break the rule of the binary search tree. So we must follow the rule of the binary search tree that as I mentioned. And the advantage of disadvantage of binary search tree is that like because the left the left is less than the parent, and the right equal to the parent. So if we want to search the element, it's just like a log of n, right? Because like for example, I want to search for the normal way, like brutal way, right? Linear search, that we have to search from beginning to the end to find the element, right? For example, I have like 10 element in the word case. I have to like search throughout this 10 element. But for the tree, for because I can compare with, for example, I want to find the number 4, right? It's gonna compare like if this number is less than 5, it's gonna go this way, right? If the number I want to search is greater than 5, it's gonna go this way. If it's less, it's gonna go this way, because right now for this scenario it's less than 5, so it's gonna go to the left, so it's never go to the right. So we have to process. So first, because the tree can have like multiple level, so we have each in each level. So this is a log of n. This is the advantage of tree, and it's more. And another advantage of tree that is the implementation of the binary search tree is simple, so because it's just like have two nodes, the left and the right, so it's easy to implement. And time complexity of the operation, as I mentioned, if you want to search the element in the tree, it's like the log of n. And if you want to insert the element, it's also be the log of n. And when we remove the element, it's the log n to travel to the node that want to remove. And it's gonna take like, I think from my understanding, because it needs to find some element to replace this position. For example, this tree, right? This is the balance tree, because all the node have like 2 children, and the leaf node have no children, so it's a balanced tree. The difference between like the left and the right is 0. So for example, if you want to remove this element, right? There are two ways to remove it. First, I can like find the leaf element on the right side, because, or I gonna find like the way this element on the left side. This is the next element right here. Also, I need to replace it to right here. So I need to travel. For example, if I want to touch like for the right, I need to travel to the end. right, to replace it. So I think it's gonna touch overall, right, because it is a plus operation. So I think it's still like 2 log of n is still like log of n in some way, I guess. I search this on the internet. Deletion, okay, it's still log of n. Deletion. In the world case, it's gonna take like O of n for Barrow trees, where it's like touch O of n. I don't understand because like it's not like travel through the tree. If it's less than, it's just go like one side, right? If this element belong to the left side, it's go like on one side, and if it's greater, it just go on this side. So it's always, it must be a log of n. Any case, even in the world case. Hmm. Let me ask my. I know now. In the world case, land is not like the balance tree, because I took example of the balance tree, but like in some way, like for the skill tree, the skill tree is like it's just like go one side like this, right? We traverse like the linked list, so it's like bit of n. I know, because this is a happy scenario that we insert this and it's like a balance tree, but if it's not like balance tree, it's called a bit of n. Okay, okay, I get it. Okay, and then I gonna provide implementations with the some basic implementations with the by research tree. I gonna erase for. I just gonna provide implementation with insertion first. So for insertion, right? For example, I already have the roots right here, right? The roots right here, and this contain like 5, for example, and then I want to insert the element 4 right here. It's gonna, because I gotta provide the data of 4, right? It's first, it's gonna compare. If it's like less than 5, it's gonna go to the left side. Otherwise, if it's greater than 5, it's gonna go to the right side. And it's gonna recursively to do, for example, for from the this is, for example, for the right side insert, which is element of 7. And if I want to insert more, right now I want to insert the element of 3, right? I provide the data is 3. How it's gonna go? First, it's gonna compare to the parent, the root. If it's less than the parent, right? It's gonna choose, right? It's gonna go to the left side only. And then in the left side, it's gonna compare again. Right now, 4 is the root, so it's gonna compare, right? If 3 is less than 4 or greater than 4, right? If it's like less than 4, it's gonna go to the left side. Otherwise, if it's greater than the left side, if it's greater than the 4, for example, like 4.5, right? It's gonna go to the right side. And we use with the recursion. And there are one escape, like when the root is null, which means like there's no element in the tree yet, so we just insert it directly. And this is the physical code. First, provide the data. We're gonna check if root equal to null. We insert directly. We create a new node, right? Create a new node with this data, and then we search the root to the data. And then also we call the recursion, right? If it's null, right? Because for example for this 4, if it goes to the left, this one is null, right? So it's gonna create the element for 4. So this is not a SK, it's always worse, so we not to be considered like if like the tree does not contain any element, and if it's null, right, it's gonna create a new element, and then assert. And I want to store the parent, so I'm gonna tell it later in the real code, but right now I just like provide the field code, right? The first step 1, right? This is the SK to stop the recursion because I'm gonna use the recursion for adding element. So if the root equal to null, we're gonna create the new element and then assert the root to the data. And then we return. I guess it should be return the data, the new node. And here I scroll the recursion. If data less than node latent root dot data, which go to the left, else if data greater than root data, we go to the right. Done. Else we return. Right, for the L, this is kind of confusing because like for me, I don't know, for my understanding, because in e recursion it's gonna go to different level. It's gonna go down, down, down. For example, right now I scroll the node, right? It's gonna return this node back to the person who calls. For example, right now for the 4, I got a root, and this root is the 4, right? Root left, root dot left equal to recursion, and it's gonna go down right here. So it's going to return something, right? Because it's going to reference for each node, it's gonna hold reference for the 2 node. So for the right now it's the left, so I just return it back to the parent. And right now because I start from this root, right? So at this point, if it's not like um, after it's returned, this one must be return something to here. So it's still 4, we not change something, so we just return the node. This is the cross. I'm gonna create the size class inside the resource tree. This is the node, right? And I call it at private. Uh, this is the modifier static, so that I can search everywhere. Class node, and inside this node is gonna contain the data of integer, and then this reference for the right, at the left and right. Done. And because I want to hold reference for the parent, so I going to create like the parent, so I can travel up, and then I call the generate I create the constructor for the node. Done. Everything done. And for the collection, the outer class, I'm gonna hold reference for the root node. Done. And then I use alright, I'm gonna call the supporter. I'm gonna use the supporter right here, and it's gonna return the node. Right now I'm gonna use a recursion. The first escape the condition. If root equal to null, I want to create a new node. And then I set the parent equal to parent. And I return the new node. Done. And for the recursion, first, right, if the root, the data less than the root dot data, we're gonna go to left of the root, right? So left equal to as element, we're gonna pass like root left data, and the parent is run out the root. Done. Else if when the data is greater than root dot data, we go to the right side. Done. Else we just return root, right? Done. I don't provide the constructor for this one for the other class, but automatically the Java provides for me, so I don't need to worry about it. So right now I'm gonna test like as an element. And I'm gonna provide the supporter as a print. I'm gonna like provide the in order. Inside void is the void, and inside it's gonna scroll another supporter. I'm gonna pass the root, write the root out there, because I don't want the user to worry about the root or keep such a root. The collection is gonna grow to scale itself, so I just provide the supporter. And for in order traverse routes, you're gonna go from the left, right, mid route, and right. Alright, so we first need to set the condition like while the route. I think it's missed some logic, I guess, because it's like print left and the right, and it's gonna lead to infinite loop. So I need to set something to. Hmm. I think it's missed something, but I already forgot it. So I'm gonna check the reference with the AI to see what's wrong with it. Ah, yeah, yeah. It's due to recursion, not like print out like this. Uh, I forgot it. Okay, right now it's will work properly. Hmm? Why I don't see anything? Let's ask my friend what's wrong. The issue with traversal methods is use a while loop instead of a recursion. Ah, I know. Right. Hmm? Oh my goodness, why? Why nothing happened? Let's see. Okay, because I want to see what happens with my code, so I gonna use with debugging. Okay, first I create a collection out of class, and then I gonna add the element into this one. Zoom into, and now we call to add element and root in none. Hmm? Do I don't see anything? Root still none. Oh, we do something wrong with the root. the root is known to data is 5. I just want to jump into the elements 5 because why it's enemy. It's not called this function. This one good, this one good, but something's wrong right here. Right. What's wrong? What's wrong with my code? For this one, root equal to as element. Oh, right. 4, 5, 7. I need to like put the root right here because it's like the recursion, so it will return to the root. For example, if I want to add an element of 3, you're gonna touch a symbol of 3 and draw it out for easy visualization. 3 is right here. Well, it's really okay. On a zoom into element 3, right now the data is 3. And the root is this one, and the noon is the parent of this node. The root. Huh? It's one to jump into. Why is it not allowing me to jump into? Jump into. Okay. The first condition in noon, right? The root in noon is 4, so it's gonna go to this recursion. I'm gonna draw it out. Like 5, 4, 7. Right, when I want to add an element 3, first I call as element 3, so it's gonna go through, it's gonna compare like this one is greater than 3 or not. It's because it's less than 3, it's gonna go to the left side, and it's gonna compare to the left side of 4 right now. And it's right here. basically this is the idea, but I want to see it step by step, so zoom into zoom into one of the rules is null. Okay, this one is true, so it's gonna come to this one. It's gonna go to the left side, right? Because it's less than 5, so it's gonna come to this node, the left side of 5. Okay, I'm gonna jump into right now the parent hold the data of 5. The root, right? The root right now is 4. Right now in null, so it's gonna create element of 3. Data is 3, and set the parent to 4 because right the parent is 4. This or what it's do, and then it's gonna return new node, and like the root left of the 4 is like the 3 is like set the condition, right? It's gonna return right here for the root right now. The root is 4, right? So it's go right now the 4 gonna return the root, gonna return like itself to the 5, right? The 4 right now the root is 4, because after like insert for the left, it's gonna go to the return root right here. It's gonna return to the 5, right? The root right now is 5, right? It just return the 4 to the its parent. Okay, it's all the whole step when we see in the debugging. And for travel, there are different kind of traversal in the registry. There are have like two main way. First is depth first travel, and the second is breadth first travel. For the depth first travel, there's like have a three variety of this traversal. First is in order, second is a post order, and three is like post order. And just the difference of three is just like the order of them, and right we just like change like the order of three. This is the depth first depth traversal. So and for the breadth, like when we gonna like traversal through the level rather than the depth. As a level, for example, the level in the tree like this. For this tree, the level at the root is 0, and the level of 4 and 7 is 1, and the level of this like a new node is 2, level 2, level 1, and level 0. So for the breadth first traversal, it's gonna like print 5 first, and then it's gonna print the level of this like 4, 7, 3, and because it's use something called like the queue, right? The queue follows the rule of like first in first out, right? So we just basically just put the parent right here, right? The root right here, right? 5, and then we call the left side like the 4, and then we call the right side is 7. Okay, and then for this one we're gonna call like the left side of 4 is 3. Done. It's gonna print this in the order, right? Because like when it's come to this right, it's like print the 3, right? When it's before it's print the 4, it's gonna push the element execute the element, execute the element like if the left is the left of 4 is different, it's not null, it's gonna execute to the queue before it like print it out. So it's just execute it like this way. It's gonna print from the left to the right. So I'm gonna provide implementation of the breakfast traversal, and for the depth first traversal, it's just there's no difference within order traversal, but just with different order. So I just did a sample of this card, so I not try full of them. First I gonna write breakfast traversal. In here I'm gonna call the supporter for this. I'm gonna pass the root, and you see why we use the supporter is that like we don't have to care about the root, which one is root. We just use the abstract class right here. That's gonna do all the things. It's gonna keep track for the root, and it must be correct if we provide it like private. The modifier or the supporter is private, which means that like the member of this class can use it only, and we cannot use it outside. Okay, so and then public void queue of the node. What? So it provides all the API for me is right here. Done. Okay, I can use linked list to hold for the queue. The queue is like the interface. Okay. We add roots first out there here. think this 3473, right? That is to print out like a level. Because according right here, the file is root, so it's gonna print the file first, and then for the level 1, it's gonna print like 47. It's currently, and then it's like print the last element trees right here. So for this order, it is already right. And another ABR is removing, and for removing, there are sometimes that we need to touch consider. Like for removing the element from the tree, there are like 3 scenarios. The first scenario like that, the remove it node, right? The remove it node is the leaf node, and it like contain because from the property of the node in a research tree, one parent, right, can have like the maximum with 2 children. So that like when we remove the node, there are some 3 scenarios that we should consider. The first case is that the parent, right, the parent not contain any children, right, contain no children, this node, the remove node is no children. The second is that like this node contain one node only, right, one children. And the third scenario is that like this node contain 2 children, right? It means that it's contain like these 2 children. So on done. So that like in size the removing the API use like we just using like the if else statement to handle these 3 scenarios. Everything is done. So the first step is that like when the client provide us with the data, like the integer that's the number that they want to remove. For example, the 3, 5, 4, 7, 3, right? And I gonna draw more like right here is 4.5. Honestly, the integer is not allowed for double, so I change this a little bit. Which one is it? I wanna using another number for easily 8, 4, 10. For the 4, I gonna insert like 3, 5, 9, and done. Okay, this is my example. So for the first scenario, for example, if the user wants to remove the number 3, it's so easy, right? It's first it's gonna compare the data with the root, right? If it's less than A, okay, it's gonna go to this node, and then it's gonna compare again. If it's like less than 4, it's gonna come to here, and then it's gonna check like if this node don't have like at the left and the right have no children, right? We just remove it directly because it's not affects any to the structure of the tree. But if they want to remove, for example, like for 5 right here, for the 5 is hold another children. What I should score it here is much greater than 4. So basically, I just put another right here is 7. Okay, it's greater than 4, less than 8, and it's greater than 5. So it's for the rule. So if the user want to remove the element of 5, for example, they just compare it like they travel to this node, and then they're gonna check like if the left is null but the right is not null, so they just replace like the parent on a point to this node directly, then just remove it, right? Done. We just set the reference of the right side of this node to leaf node, right? To leaf node of 7, and um, for this one we just remove it. We just not hold the reference, so the garbage collection is gonna take care of this node for us. It's gonna automatically remove it inside the memory. Okay, and the third scenario is like when we want to remove the node with two children. For example, right now I want to remove the number 4, right? So it's gonna go to the right side. There are two ways that we can remove the element of this. So for example, I just want to remove the number of 8, the root node, right? It's gonna just like it's gonna need to have some element. When we remove the elements A, it needs to have some element to be the root, right? To some element to replace this position. So there are two ways. The first way is that like we want to replace with the leaf element on the right side, right? For this tree, we can replace with the 9 right here, and it's still like the for the rule, right? Is that in this way, the 9 is still less than 10, but still greater than whole left side because it's from the right side, so it's still greater than the left side. Then otherwise we choose the greater number on the right side. From the right side, right here, 4 is greater, so we just put the 4 right here. So 4 is still less than 10, but still greater than 3. The greater is right now is 7, right? I'm gonna travel to the right side from the left to get the greater element. Right here is the 7, right? I'm gonna touch the 7 element right here. 7 is greater than 4, 3, 5, right? But still less than the whole right side. And there's up to us to choose one way, like choosing the leaf element on the right side or choosing the greatest element on the left side, because both of them is the leaf node, right? So it's not affects the structure, which replace the data directly like this way. So I'm gonna draw the code, write out the code right here. Publish fry remove. So first we're gonna travel to this node, right? If for remove elements, I want to change the parent, so I'm gonna pass like the new right here, and for the second it's a like the parent, and this is the current node, right? So it's more intuitive to use it like this way, and I gonna check if the current the data, and the user gonna pass like another variable is like I forgot it, like they're gonna choose which element to remove this, and it's good at the data. Okay. I'm gonna check like if the current dot data is greater than the data, so we're gonna go to the left side. I honestly don't remember. It is like the way to implement it. Like actually, hmm, it's gonna traverse to the element that I want to find yet right now. What's I switch? Uh, okay, this is like step one. When it's this is the case when it hits like the leaf node but still don't find the removing data, we just like return null. Right, using the like for if right now it's not like static anyway. It looks so dummy in some way, but anyway. When I get the current, it's not like the right way. I guess it's not like the right way because it's just return and not doing anything. How I can like steal the whole the reference for the removing node? I gonna like okay, it's gonna stop. When it's fires, it's gonna return to the left, and then it's gonna do some more steps right now. If don't know, because like if return for the left, so right now the current is the parent of the removing node. So I don't know like the removing node on the left side or the right side. Mm, I need to use like the reference right now. Right here. It's gonna check if the tree is empty. It's gonna like return noon. Oh, this is the LK. When it's already equal, I'm gonna do like L for the L, which means that okay. So that's we're gonna handle tsk if the current dot data dot left equal noon and current dot right then the noon. We just like change the parent's reference, right? The current dot parent, we just return the noon to the parent. Done. Okay, not need to change anything. We just return noon to the parent. And then if k2 right, if we have one drive, this drive can be on the left or can be on the right. If like current dot left it different noon, which means that like it have to chill on the right. We just like change the current dot right dot parent equal to we change the reference, right? Well, first we just um, change the parent for the replaced node, right? Because for as you know, like for example for the tree, let's I want to respond to node of 5. Right now the parent of 7 is 5, so I just want to change the parent of 7 to 4. So I set it like the current is now 7, the current parent is 5, right? And then I current parent current for I want to remove the number 5, so the current right is 7, and then I dot parent. It means I want to change the parent of 7. I change the parent to 4, which means that the current dot parent, right? The current dot parent. So after do that, I just basically return the current dot right. Okay, because on the right side I'm gonna return for the 4 I'm gonna return the 7 directly, not return 5, right? If done, and then another else case, else if done, right? Otherwise, when the remove the nodes, I have the children on the left side, we just do something opposite, but the logic is still the same. No, nothing opposite here, just be the difference keyword. The logic is the same. Case 3, when remove this node, have 2 children, right? First, we need to travel to find the, for example, when I want to find the greatest number on the right side, at the smallest number on the right side. So I using another support function, right? Node smallest on right side, right? I call find smallest on right, and I pass the current dot right. Okay. I call the support function private node and find smallest function, and it receives the node, right? Square and dot left. Done, right? It's gonna travel to the left side. Why I travel to the left or the right? Because like for the right now, if I want to travel to the right, it's always greater and greater. But if I want to I travel to the left, it's gonna get the minimum element of the right side. So for example, I want to the left of 10, it's in 9, so it's a small element on the right side. It's all the things that we want to do. Done. When we fire it, we change the value, right? Like current dot data equal to smallest. Done. We transfer the data, and then we remove the leaf nodes from the tree, right? The third step after transfer the data right now, right? The data 9 right now. Transfer the data. I insert the new data for the roots in 9, right? I not transfer the reference because it's easy to transfer the data, right? But then doing manipulate transferring the reference for each of them is easy right now for this scenario to transfer the data. And then I remove the node. Right now it's still like the whole like the reference to 9, and you know this one holds have no joy, right? So I just call it like I just call to the smoothest element. I pass the data. No, I pass the force here. I pass the current. No, what I supposed to push right here, the current. don't know this is the right way to handle with. It's gonna return back to the current. From the current, from the from this current, I want to return back. Okay, it's good. It's good though. I think it should work. Basically, it should work. I want to remove element A, and then I finish out. Let's see. It should work. Oh, it don't have like A. Hmm. Something is wrong. That's my function not work. Hmm. Something's wrong with my code. Okay, it's work right now. This should work on the right subtree. Oh yeah. Right. Because it should work on the right subtree. We update for the right subtree. Everything done. I think it should score as well. The current right reasonable element. Done. I think that's all about Paris surgery. Till now, all things that I know. Spice means mask, yes, high chest. Okay, it's done for now.